Woohoo! We're super close to the end of our quadratic functions unit. Woohoo! So the last few lessons that we're going to have are going to be dealing with gravity. So gravity is predictable. How amazing is that? Well, let's get into our story and see how it's predictable. So Galileo Galilei found that gravity exerts force on any free-falling object that the distance fallen in feet, d, is related to time by this function right here. He created this function. So suppose an object drops from a height of 120 feet. Okay. How much does it fall in 0.5 seconds? Okay. So what we're going to do is we're going to take our equation here, d equals 16t squared, where t is time. So we already know what the time is, which is 0.5 seconds. So we're going to put that 0.5 seconds squared, and we're going to bring everything else down. So 0.5 times 0.5 is going to give me 2.5. I'm sorry, 0.25. My bad. And now I'm going to multiply that by 16. So go ahead and use your calculator. All right. So the distance fallen is 4 feet. So how much did it fall in 0.5 seconds? It fell 4 feet in 0.5 seconds. So if you don't know how tall 4 feet is, I'm about 5'5", so maybe up to about my waist or my belly button. I have no idea. Take your height, cut it in half possibly, if you're 6 foot. Or not, But how many seconds pass before it hits the ground? So we are instantly given that this item or object is dropped from 120 feet. So I know that this is actually my d. So I have d equals 16t squared. I'm going to figure out how many seconds passed. So what I'm going to do is take that 120 and put it for my distance, since I already know what it is. So the first thing I need to do is take 120 and divide it by 16. I need to get rid of the 16 first. So if I take 120 and divide it by 16, so go ahead and plug that in your calculator, you should get 7.5 equals t squared. Here, let me move it up. So 7.5 equals t squared. Well, I'm not done yet. This squared I need to get rid of so I know the exact time. So the opposite of a square is a square root. This might be all coming back to you ever so slowly. If you took the square root of it, it is going to be, the time is going to be 2.73 seconds. So this is how fast before the ball or object hits the ground. It's going to take about 2.73 seconds before it hits that ground, falling from 120 feet. Holy cow! That's super fast. That's like almost blinking. But let's see. So we're going to complete and we're going to choose points various times between 0 and 4 seconds. So I want to choose 0. Let's choose 1, 1.5. Let's do 2. And let's do 3. Why not? Let's throw one number in there. Actually, let's do 2 point. Let's do like 2 point. Because I already know it's going to hit the ground at 2.73 seconds. So let's do like 2.5. Why not? Let's see how high it is above the ground. So what we're going to do is the distance fallen. So what we're going to do is we're going to take the formula 16t squared, and we're going to plug in time for t and see how far it's fallen. So I have 16 times 0, which is going to be absolutely 0. So it's not even fallen yet because it hasn't even started. So I know the original height is 120 feet, just like in the last problem. All right, so now I have 1 second. So now I'm going to take 16, multiply it by 1, and square 1. So what we have now, which we have is 16 times 1, which is just 16. So what I'm going to do is going to take my original height, 120, and subtract it from the 16 that I have, because that's how far it fell, right? So 120 minus 16 is going to give me 84. So it's 84 feet high still. Okay. So now I'm going to take 1.5. So 16 times 1.5 squared. So 1.5 squared is going to give me 2.25. And I still need to multiply it by that 16, which is going to give me 36. So the reason I'm subtracting the equation, essentially, is because I know that my distance fallen is already 36 feet. So what I'm doing is subtracting how far it fell from the original to see where it is. And what we get is... Whoops, sorry, I'm already got ahead of myself. It's 84. This one up here, sorry, I messed up. It's 104. I got a little too excited. So now I have 16 squared, or sorry, 16 times 2 squared. Well, 2 squared is 4. So I'm going to multiply 16 times 4, and that is going to give me 64. So again, subtract 120 from 64, because remember it's falling, and that's going to give me 56. All right, now let's do the last one. 2.5 squared. 2.5 times itself is going to give me 6.25. Multiply it also by 16, because we need to figure out how it's fallen, and that is 100. Oops. Some nice, easy, nice numbers, right? So 120 minus 100 is going to be 20. So the height is 20 feet above the ground. Perfect. All right, so now that we figured that out, what we're going to do is we need to figure out which equation would match the object's height at time t, represented by our function. So looking back at our table here, which equation do you think is going to match? Well, let's start with the far one here. Negative 16t squared minus 120. Well, I can instantly know that this cannot be it, because the negative 120 means it's below the ground. We're falling, an object is falling, so it means it needs to come up, so in the positive y's. So this can't be it. All right, so let's look at the second one here. Ooh, I have a positive 120 because this is my initial starting. This is where I start at. And my slope is 16t squared. Well, I'm actually dropping an object, not throwing an object. So this equation would work if we were throwing an object. But since we're having an object fall, this cannot be it because it's positive 16, meaning it would increase, it would go up. So let's look at this one right here. I have 120t squared minus 16. Well, I can instantly know this is not going to be it. Yes, it does have both of the numbers. Yeah, it does have the t squared, but we're not starting 16 feet below. These numbers are switched. So that means that our equation for this is 120 minus 16t squared. And to prove it, I can take 120 minus 16 in the, let's do 1 second, squared. 1 squared is 16. So essentially, what we have here matches what we did in our table. So that is the equation for when an object is falling. Whatever the height is, minus 16t squared. Keep this negative 16t squared in mind, especially for tomorrow. So I'm going to actually graph it for you. So if we graphed this equation, it's going to be super hard to see, so I'll zoom in a second. So 120 minus 16t. So obviously it's going to start all the way at 120, and it looks like that's going to be our vertex, because guess what? That's where it's starting. We're launching it down. We're dropping it. And as I can see, I'm only going to be looking at the right side of my graph here because, remember, I'm dropping an object. It doesn't really matter on the other side of my parabola at this point. So if I continue to go down, we can keep going and going and going and see at 1 second we did have 104 height, and we keep going and keep going, and we can see at 2, let's keep going, at 2 seconds down here. This graph is super long because we're falling from 120 feet. Keep going, keep going. At 2 seconds, if it'll match up perfectly, we have a height of 56, which is what we got. And if we keep scrolling down, it'll eventually hit my y-axis, or sorry, my x-axis at 2.739 seconds, which is exactly what we had on the other one. I believe we didn't write the 9 after the 3, just because, well, whoops. Yeah, we didn't write the 9 after the 3. But we can definitely see that is why the equation is what it is. And if you don't believe me, you can plug in 1 for each of these equations and see that this will not be the same answer. So now what you're going to do is you're going to complete checkpoint 7, falling objects in 2 graphs. You're going to compare 2 graphs and talk about how one specifically matches only one type. So we're going to be comparing graphs.